Hey everybody, my name is Rob Lamandola. Again, I'm an applications engineer here at SMA America. Been over here for a little over 3.5 years, and really I'm a technical specialist on our home and business solutions. I came prior to SMA from the EPC side of the business, so as an installer for about 7 years in a lot of variety of roles, both residential and commercial. So I think like an installer, I know, the perspective you have when you're looking at, purchasing equipment and providing that equipment to your customers for long-term reliability. And today we're excited to talk to you about SMA's ShadeFix optimized string inverter solutions. Hopefully everyone can see the screen. This is me. And as you probably know, all of the information we're going through today is available and more on SMA's website, sma-america.com. And if you ever have any questions, technical or training related, you can reach out to Justin or contact us at training@sma-america.com. We have trainings every week via our Solar Academy. So please, go to our website and register for additional trainings as they come. So out there, I know we probably have a variety of folks on the call, installers that are doing residential and commercial designs and installations, probably, not just on the West Coast, but maybe a variety of locations in the United States. If you're not yet using SMA for your projects, and you're using some of our rival equipment out there, I guess I would pose the question, do you find yourself having to go back to your installations, not only once, twice, but maybe multiple times to replace poor quality inverters or, rooftop electronics like microinverters or optimizers? If you kind of fall in that boat and you know that it's causing frustration for your customers and yourself, because it's basically a unpredicted service call you didn't want to do, then you're in the right place. SMA has great solutions on the residential and commercial scale that are code compliant. We offer module level rapid shutdown if that's needed for your rooftop projects. And if you forgot, we don't need those complex electronics for ground mounts or carports in a lot of areas. So great thing about SMA inverters is if you don't need module level shutdown, then you don't need to purchase it or install it with our equipment. If you do need it, we have the most reliable options for you. So let's start with some building blocks of, what equipment are we talking about, and also go back a little bit to the basics of PV and solar, how modules work, and how that really helps our ShadeFix technology provide you a optimized solution that can deal with shade and various rooftop designs, again, without using microinverters or complex traditional optimizers. So we'll start with our Sunny Boy. Here you may be familiar with the Sunny Boy US-41. It comes in a variety of power classes. It gives you all the tools you need to create a system that's optimized, both again around shade and multiple azimuth and tilts for complex roofs, without the need for traditional optimizers. So we have 3 independent MPPT channels that, think of those as 3 optimizers built right into the inverter. Each of those channels has a very wide operating voltage window. So that translates to the ability to have long strings, short strings, and just give you flexibility for design. Integrated DC disconnect, the ShadeFix string level optimization MPPT algorithm is built in. We have now integrated SunSpec rapid shutdown transmitters in our Sunny Boys. So there's no extra communications equipment that you might have used over the past few years. So a comms cable up to the roof is not required anymore. All the Sunny Boys have built-in Ethernet and Wi-Fi communications to make it easy to connect to the customer's internet. And when you're commissioning in certain jurisdictions, we try and make it easy for setting utility required smart inverter settings. So if you're in California, you have a drop down to choose California Rule 21 versus on the East Coast, easy drop down menus for ISO New England settings. Building on the Sunny Boy, when you move into the commercial solar install space, the Sunny Tri-Power Core 1 has been just a blockbuster inverter over the past few years. It's the #1 selling commercial inverter in the US over the past year. This is a 1,000-volt DC rated inverter. So instead of 3 MPPTs like the Sunny Boy, the Core 1 has 6 independent MPPT channels with 2 string inputs per channel. So up to 12 strings can plug directly into this inverter. So that's 6 built-in optimizers to help you deal with complex designs, or for you not to have to worry about if you have partial shade from an HVAC unit or a parapet wall for a couple hours during the day. Ultra wide operating voltage window like the Sunny Boy. The Core 1 connects to an AC type grid that's 277 480Y, right? So for most commercial buildings, this is a direct tie-in. If you have smaller commercial buildings with 208 type grids, we would recommend, and it's still very cost effective, to choose a step down transformer. So 480 to 208 to make that match. The Core 1 has integrated AC and DC disconnects. It has the built-in ShadeFix optimization algorithm. It also has the same built-in SunSpec transmitter, so no extra communications when you're communicating to our rapid shutdown receivers, and the same integrated communications. So with the Sunny Boy and the Core 1 as your kind of building block for your design and installs, you should know that the built-in SunSpec transmitter really makes it easy for not just communication setup, but also commissioning. So this is really giving you the lowest cost, lowest complexity setup for your systems. When you put a SunSpec rapid shutdown transmitter behind each module on the roof, it is still the simplest, most reliable device on the market today. The last thing you want to do after you build your portfolio of systems is have to roll trucks to replace electronics on the roof. And by choosing SMA, you're reducing that to the lowest level. By choosing traditional optimization or microinverters, the complexity you're putting behind each solar module increases drastically, and that just results in unpredicted truck rolls to replace those devices. Those devices are in, the environment and the locations that your crews really don't want to get into. So they're never, on the corner of the array. They're typically, in the middle of the array, tough to locate, tough to replace. So again, by choosing SMA, you're keeping the heavy lifting, if you will, down at the inverter level. In exchange, that leads to less truck rolls, higher reliability systems for you and your customers. So the question is, especially if your teams are used to using some of the rival solutions out there like microinverters or traditional optimizers, is, well, what about, the statement I've heard, which is a string inverter is only as good as its least producing panel. So if one of the solar panels gets shade, doesn't that create a zero energy production on the string? So kind of like the Christmas lights theory. Our competitors will say if one of those Christmas lights goes out with your string inverter, the whole system goes down. So that is false. And the preceding slides will talk about why that's false. But the takeaway from this slide is, what is SMA ShadeFix and how is it solving my concern of, if I have one shaded module or solar panel, my whole system is going to create zero production. So ShadeFix is a combination of advanced maximum power point tracking algorithms and a global sweep function that optimizes against shade. So it's built into every SMA inverter and has been for quite a while. Paired with the wide operating voltage windows of these inverters and the several MPPTs we give you per inverter, ShadeFix ensures maximum production for both your resi and commercial jobs without the need of putting traditional optimizers up on the roof. Finally, ShadeFix ensures the inverter works each string / MPPT channel to the highest energy point. So it is not the point of the weakest module that you may be used to seeing on marketing from our competitors. Even if there's shade, we can work around that shade with the tools we give you. So here's another visual of what we're talking about. And I think the basis of this and what you can find on SMA's website is a recent study that was conducted over at the University of Southern Denmark that did a year-long study comparing SMA's inverters to inverters with optimization to one of our #1 rivals that has traditional optimizers. And across that study, what the results tell us is SMA ShadeFix, with the tools we give you, outperforms and creates more energy in the majority of situations versus traditional optimizers. So this chart from left to right is really telling us that. ShadeFix on the left, which is the orange bar, versus the gray bar on the right, which is representative of traditional optimizers, is the overall yield. So in normal weather, no hard shading, SMA's solution yields more energy over the year. If you have minimal shading, so let's say from a chimney or an HVAC unit, SMA's ShadeFix solution still yields a higher energy amount than conventional module optimizers. Now we get into maybe some more real life situations, especially for complex residential systems where you have multiple trees, a chimney or a dormer. So you have hard shading moving around for multiple hours during the day. While the spread reduces, SMA ShadeFix can still perform just as well as module optimization here. It's only in the minority of PV designs or systems that you'll be installing where you're putting an array in a very heavily shaded area for the majority of the time. Do optimizers or microinverters really make sense? So the big takeaway here is don't believe the kind of marketing that some of the rivals stay out there that if one module is shaded, the system goes down. That's patently false, and we have a lot of data to back that up. So for the folks on the call that maybe have been in the solar industry for quite a while, or for the folks that are a little bit newer to the industry, I want to talk about what's the inverter seeing. So you take modules off the pallet, you string them together. Sometimes you have a string of 12, sometimes you have a string of 18 modules. When you connect those modules in series, at the end you have voltage, and when the inverter turns on, you have current. But what is the inverter doing, and what is it seeing? And when there's shade, what's this ShadeFix algorithm doing? So over the next few slides, I'm going to explain that. So what we see here on the right is a chart. On the y-axis on the left, we have current. On the x-axis across the bottom, we have DC voltage. And over on the right, we have power. That's DC power. So that's just your voltage times your current. So when you string, in this case, 5 modules together, you're adding the voltage. So if each module has 40 volts times 5, you're going to have 200 volts. And on average, let's say these modules have a operating current of close to 7 amps. When you string those together, the inverter sees this curve. So this is what a power curve looks like in the red, and an IV curve looks like in the blue. And what the inverter does is it starts to pull power off of this curve, and it decides, the inverter decides, where it should choose on this curve to operate to make the most amount of power. The inverter's job is kind of simple if you think of it. It's trying to make the most amount of power possible over the longest amount of time, hopefully in our case 20 years, without ever causing you or the customer an issue. So this is a simple IV curve. It goes up and down based on the irradiance, right? So if you have good full irradiance, the current will be high. If the irradiance goes down, the modules can only output maybe a lower current or a lower power. But what the module gives our inverter is what we can choose to make energy with. If there's an optimizer behind a solar module and the module is totally shaded, whatever the module can give that optimizer is what that optimizer can use. So optimizers do not magically make power. It always starts here at the foundation, which is what's the voltage and current that the module is giving to us to use. So here, we're kind of taking that concept a little bit further. So the inverter completes this circuit, and it's important to understand that the inverter controls where on this curve it gets to operate and make the most power. So it must be within the inverter's operating window, and that's why SMA inverters have such a wide window, right? This green vertical line really represents our low voltage operating limit, all the way up to 600 volts operating for commercial, for residential, and 1,000 volts for commercial. So by keeping this low limit, SMA's inverters have the flexibility, especially when shade or variety of situations happen on this string, to choose along this voltage x-axis where it wants to make power. That's a key point. Okay, so now that we've built in our minds how the inverters are operating and choosing where to make power, I want to go back to a very critical piece of information about how modules work and why the modules themselves have built-in shade mitigation. And that relates to bypass diodes. So many people forgot that right in a solar module or a solar panel, we have bypass diodes. A majority of modules have 3, but as modules have advanced, especially split cell modules or redundant busbar modules, the modules features, 6 bypass diodes or redundant bus bars, are actually making traditional optimizers less and less valuable. So that's a big advantage for the SMA solution. So you say, what does a bypass diode do? So the takeaway from this slide, which is broken into the top section, which is a normal solar cell operating and allowing current to flow, versus the bottom section, which shows a shaded solar cell, is what's the bypass diode doing for us? So starting from the left, the current is flowing through the solar cells. And in this case, it flows normally through these 4 solar cells. The 2 cells on the left have a bypass diode, and the 2 on the right have a bypass diode. So what happens when you shade, in this lower section, the 3rd solar cell? This is kind of a micro level of what's happening. So when you shade the cell for a split second, that shaded cell becomes a blockage. So think of like a traffic jam. So there's a small traffic jam, and that creates resistance. And what the bypass diode's job is to reroute traffic around the traffic jam. So that's representative of this red arrow here. So when there's shade here, we get resistance on the solar cell or solar module, and the bypass diode serves as a traffic cop, or let's say a pressure relief valve, to allow that blocked current to avoid the shaded section and travel around it. So this is really disproving the myth that if you have shade, all current stops there and your power goes to zero. No, if you weren't aware, you have that functionality built into every solar module you've been installing. So when the module is shaded, the current reroutes around that shaded section if the resistance is high enough. So here's another way to look at it. So here we see a visual of a traditional solar panel or solar module. You have your cells, and typically you have 3 bypass diodes. Each diode allows it to act as a traffic cop or pressure relief valve for a third of the module. So we have the left third, the middle third, and the right side or right third of the module. So if any section of this first third is shaded, that bypass diode will allow current to bypass or jump over that shaded section and flow through section 2 and 3. And this is really how SMA ShadeFix algorithm works in tandem with the modules you've installed to pull the most power off of the non-shaded sections. So here again, we're seeing, okay, what's happening when a module has no shade? The current flows through all cells on the module. The bypass diodes are not active. And what happens when that module is shaded? So there's a hard shade object here, let's say from a chimney or a pole. So the current flows through sections 1 and 2, and then the bypass diode for section 3 allows that current to jump over or bypass the shaded section. So we're not being pulled down. The IV curve is not being pulled down and negatively affected by that shaded section. And this is all without traditional optimizers. So again, we say ShadeFix, we're busting the myth, which is the myth of the weakest module in the string will draw that string energy or power down to zero. That is basically false. So now you know when you put a string of modules together, you know that's creating an IV curve, you know that's creating a power curve, and depending on what that curve looks like, the SMA inverter can always choose a maximum point in which it can pull power off that curve, even if there's shade on certain modules at certain times and other modules during other times. So we'll start here again with an unshaded array. These speedometers represent the power output of each of these modules in a non-shaded condition. So you can see here, everything's at full power or full speed, and this is where the curve is. The inverter is choosing to pull power at this inflection point here, whereas basically the highest voltage and highest current level, which is the highest power. So we say, okay, what happens, early in the morning or late in the afternoon when a chimney or a pole is casting shade on some of my array? Don't I need traditional optimizers for that? No, you do not. So here we have full speed or full power from the first 5 modules, but the 6th module has a hard shade over it. So you know that if that was a 350 watt module, basically that would be almost fully blocked. So let's say that module contributes 0 to the rest of the string. So what happens is the voltage curve or the voltage side of the equation actually reduced by 30 volts. So this module used to contribute 30 volts to the string, but by being fully shaded, it's basically out of the equation. The bypass diodes are jumping over all 3 sections of that module. So we're losing 30 volts of potential. That's okay for the SMA inverter. The SMA inverter sees that shift and is still able to keep pulling maximum power off the remaining 5 modules. So when we have hard shade on a string inverter, Does the string go to 0? No. The answer is no. We're still able to effectively pull power off the rest of that string. So another case scenario would be, instead of hard shade on one module, let's talk about, soft shade or partial shade over several modules. So we have that same string of 6 modules. Now the right 2 to 2 1/4 module have partial shade, let's say from diffuse shade from a tree nearby. How is that affecting the array? And then how does the inverter deal with that? And so here we see full speed or power from modules 1 through 4, but then modules 5 and 6, instead of being fully blocked by a hard shaded object, this partial shade or diffuse irradiance causes those modules to not drop to 0, but drop to a lower power potential. And we see that translated down on our IV curve in the form of not a loss of complete voltage, but we get humps in our IV and power curves. And what's happening here? So as the irradiance lowered on these 2 modules, their potential contribution is basically lowered. So now the inverter kind of has a tricky job to do. It says, well, I have a maximum power point at 0.1, I have a maximum power point at 0.2, which one's the best? And SMA's advanced MPPT ShadeFix algorithm is great at figuring out where to operate to pull still the most amount of power from the string. So while we look at the local points to choose a maximum power point, we also scan the whole curve to make sure that we're not missing 0.1 or 0.2. And that's called a global sweep or a full sweep. That's what ShadeFix is doing. And it allows us to really close the gap between what we provide automatically in our inverter versus what traditional optimizers provide. So that advantage that those optimizers used to provide when compared to old single MPPT, basic MPPT inverters is really minimized when we have this advanced MPPT ShadeFix algorithm. And you can see that here. Here's just a close-up of that diffuse irradiance or partial shade on this module. So in this partial shade condition, because the cells aren't blocked by a hard shade, so a 0 irradiance, in this case, the bypass diodes do not come into action or reroute the current around the module. The current just goes from 7 to 6.7 or some lower current. So there's not enough resistance to kick those bypass diodes into action, but the curve still deforms and the inverter can still pull the same amount of power from it. Here at a shaded module with more partial shade, again, you can see that the current drives down. So from 7 to 6 down to 4.8. It's still not causing the bypass diodes to jump into action. But you can see on this heavily shaded module, we are at 0.2 on the curve. Again, just visually trying to get us into the operation of what's happening up on the arrays and strings that you're installing, to make it crystal clear that for your systems, if you have partial shade or complex arrays, you do not need traditional optimizers to still pull as much power as you can from the system. So we're going to jump out a little bit. So come out from the modules point of view and the strings point of view, and just give you a big picture of, again, what's happening on your array. So here on the right, we have a visualization of current flowing through the cells on a module. So just like we showed before, in and out of each module across those 3 or 6 bypass diodes. Normal weather, the electrons pass freely right through the array. the modules are giving us full power potential. Here in a partially shaded array, so we're representing this by just showing a leaf, or multiple leaves from a tree falling on the module. All the modules, in this case are saying, oh yeah, if one leaf falls on one module, the current is going to be blocked or limited through the whole array. And now, as educated solar professionals, if you hadn't already, that is really a myth. So one leaf falling on a module doesn't knock your whole string out. What is true is happening on the bottom, which is if a hard shade object like a leaf or something falls on a portion of the module, the bypass diodes kick in. They act as a traffic cop or a pressure relief valve to reroute the current around this blocked section, and the rest of the modules can produce full current. And the SMA inverters can pull that power off of the string to make you the most amount of energy possible. So the next question is, well, I heard that traditional optimizers or microinverters will still produce more power, more energy over time. So won't adding those complex electronics make the system produce more? So the takeaway from this slide is really starting to get into how those complex MLPEs, module level power electronics, work. And it's really not always what it turns out to be from the marketing that you hear. And so on the right, we have 3 scenarios, again, representative of a basic array with 8 modules, no shading, hard shading, and partial shading, and what those traditional optimizers are doing, and how it's not always the greatest situation, both in operation and for long-term reliability. So in a non-shaded situation, those traditional optimizers are still doing work behind each module. So they have the capability to buck and boost voltage that's coming into their optimizer units from the module, and they're cycling, right? So no matter what happens, they're getting warm, so they're generating heat. They're knocking you with an efficiency loss. And if there's no shade, they're still operating. They're still doing something up there. And that's every day, all year long. And that's a concern when you talk about long-term reliability. So for non-shaded arrays, you would say, well, okay, Rob, I guess you've proved to me that traditional optimizers are not needed. But here you have a hard shaded situation. So in a hard shaded situation, that optimizer, again, cannot magically make power from a module that's not giving it any power. So this is showing that optimizer really shuts off. So there's no power from the module to power it up. So it bypasses over just like it would if it wasn't there, because we have bypass diodes. But what happens to the rest of those optimizers? They actually have to boost the voltage because they just lost 30 volts to make the inverter happy. And again, that's running those optimizers in basically a cycling state. For long-term reliability, that's a concern. Thirdly, where most people think traditional optimizers help, which is in partially shaded conditions. You see here that in partial shade, those optimizers have to push voltage down or buck voltage to bring the current back up with the neighboring units. The main takeaway here is whatever happens up on the roof with traditional optimization or microinverters, they're always cycling, always generating heat. And what that typically leads to over time is more truck rolls to service those components. What SMA, on the contrary, is providing you is a much simpler device on the roof So it's a purely rapid shutdown device. It's allowing current to pass through normally. So it's not generating any heat. It's not giving you an efficiency hit like the rival products are. And the inverter is still able to deal with non-shade, hard shade, and partial shade. What's a good analogy for all this? If you see here, a lot of you guys, and gals probably drive trucks, whether it's for work or for play. What SMA provides is on the right, which is kind of like a on-demand all-wheel drive, right? So in normal conditions, we'll say non-shaded conditions, you're not really having to do any heavy lifting. So you're working smarter, the inverter is able to do what it does best, produce the most power, and you're not having any heavy electronics on the roof, in most of your situations. Contrary to on the left, this is non-SMA, right? This is traditional optimization. It's really like having your four-wheel drive of your pickup truck on 24 hours a day or all the time you're driving, even if it's not slippery, icy, rainy outside. You're taking a loss on your efficiency because you have all four tires running, even though it's not slippery out. Your miles per gallon go down, and it's really a lot of overkill for situations that you don't need it, right? So when does it get really muddy where you need to turn on that four-wheel drive? It doesn't happen too often. What SMA is giving you on the right is really the best of both worlds. So two-wheel drive 90% of the time when you need it. And then when you do have shade or tricky situations, we have that ShadeFix algorithm to help you out. In conclusion, on the topic of ShadeFix, I know there's a lot of words on this slide. Again, the takeaway here is not only has SMA done its own internal studies, and we continue to do long-term studies of should we use MLPE or not, and our studies prove that the benefit really is not there. This study that we published recently on our website was completed by University of Southern Denmark over a year. It was titled The Impact of Optimizers or MLPE for Solar Modules. And the takeaway from this was, just like we learned over the past several slides, that SMA ShadeFix optimized system, so system level optimization, that's our MPPTs, ShadeFix algorithm, and module bypass diodes, produced more kilowatt hours of energy over the year-long study than either MLPE system. Second point here in the middle, ShadeFix optimized systems produced more kilowatt hours AC, even though the spec sheets, if you were to compare the spec sheets of SMA versus our competitors, showed that SMA did not have the highest stated efficiency. So we say, well, I thought if I look at the spec sheet and I pick the solution with the highest efficiency, I'm going to get the most amount of energy. Well, efficiency is just one small, data point in your whole overall equation. It does not represent, all the real world situations that your systems have, over their life. So for PV arrays without nearby shading or with shade objects, the takeaway again is SMA's solutions outperform traditional MLPE systems on sunny and overcast days. So with that, I'm looking at my watch here. We have about 10 minutes to cover a few more slides I wanted to go through just to build out the picture of what our solutions can offer you, especially related to rapid shutdown. And then we'll open it up for about 10 minutes of Q&A. If you do have questions, I would ask you to enter those in writing in the Q&A box. And Justin and Carlo will help me get to the questions once we get to that point. So I know I talked a lot here, but let's get back to some basics here. You have a commercial design or a commercial system coming up. What components do you need for an SMA system? It's really simple. It's 3 components. The core 1 inverter, whichever size that you choose to match up to your project. If you're on a ground mount or a carport, oftentimes the inverter is all that's needed. So you don't need our SunSpec level or SunSpec compatible rapid shutdown devices, right? So that's a great benefit of SMA. If you don't need rapid shutdown per code, you don't need to purchase these electronics, less upfront costs, less service costs, versus some of our rivals. If you are on a roof, you're choosing the core 1, the SMA compatible rapid shutdown device, and the third component, which we often recommend, is the SMA data manager. When you install the inverter and the SunSpec rapid shutdown device, do you need extra communication boxes or communication wiring to have the inverter talk to these devices to have them shut down? No, we eliminated that by installing in all of our inverters now an integrated SunSpec transmitter. For ground mounts, you just leave it off. For roof mounts, you turn it on through the installation assistant, and it now talks to those rapid shutdown devices behind each module to give you code compliance. So under normal operation, that transmitter is telling these receivers everything's fine through a keep alive signal. If that signal is lost, meaning when the AC disconnect or the power is lost to the building or AC disconnect is turned off, AKA a firefighter or first responder comes to the building and shuts off the system, that signal is lost from the DC lines, and all of these devices go into a rapid shutdown mode. So here's just another visual of that for our residential inverter, the Sunny Boy. So we're showing here on the right, the Sunny Boy power classes, the 3 MPPTs, the built-in SunSpec transmitter, and then, for example, 3 strings up on a roof, each solar module being equipped with, this is our latest rapid shutdown unit called the JMS-F, 1 per module installed on each module. So this is a real basic setup of what you would choose and what materials you would need to have a code compliant rooftop system with module level shutdown. That will give you NEC 2014, 2017, or NEC 2020 compliance. Jump over to a little bit bigger commercial system. Again, this is just showing the flexibility of the Core 1 and that you have 6 independent MPPT channels. You can have long strings, short strings, and that SunSpec transmitter is built right into the inverter, which is shown here on this slide. Again, sending that keep alive signal over the DC home run lines to the SMA rapid shutdown receivers, whether that's the JMS-F, the TS4R-F, and in the future, we foresee adding some other compatible SunSpec shutdown receivers. It's a real simple solution, not only easy to install, but extremely easy to commission. Again, we are not having to map these devices. It's a install, code compliant, highly reliable system. So I think with that, I'm going to pull out of the presentation. I'll actually proceed through a few slides, and we'll get ready to start to scan our questions and start to answer some of the questions you guys have out there. We can go back to some of these slides if you want, but yeah, hopefully what we went through today was very valuable. I hope I either confirmed or had you discover something you didn't realize about solar systems and how they operate. And yeah, thanks for paying attention.